Good morning, everyone. Hope everybody's doing well. We got that rain yesterday, and that was actually kind of nice. I got a little bit wet going to choir rehearsal, but it was nice. It settled everything. So hopefully that was pleasant to everybody. Maybe bringing a little bit of cooler weather. Um, like I say, I guess we got a nice rain, not torrential downpour, but very comfortable. Um, what we saw from the last lecture is that we were able to create lots of new identities that will definitely have an impact on us as you all move into the calculus sequence. Again, hopefully that was an interesting lecture in the sense that we just take what we know and we rework it. And lots of times when you study something and you make some adjustments to the theory and you rewrite things in ways that maybe you didn't think about, it turns out that you create mathematics that's very useful. That is, you look at the trig functions in a different way. And by opening the door to more identities, you have more tools to solve problems. So it's really nice to know what it means when you take the sine of a sum of two angles, or the cosine of the difference of two angles, or the cosine of the double angle, or the cosine, for instance, of the half angle. I mean, these are all things that we really need to know something about. And really, what creates the environment for these identities is just solving new problems. So the interesting thing about math is that what math we have was basically used to further the science of math and then to actually solve problems. And so as new math is created, it's usually because a problem is presented that requires some new tools. But of course, there's so much math out there. When new math is created, it can be very arduous because, of course, it's got to be consistent with what's already been presented. And so that's like a double whammy when it comes to working in research. But one thing that's good about math, as in any STEM profession, is that you can always rework things and look at them from different viewpoints. And that's really what you do as math students, and that you will continue to do as STEM majors, and then, of course, into your professional careers. So how do we finish up trig? Well, we finish up trig by talking about solving equations. We've already been solving equations, but we just want to apply some tools that we applied to solving equations in college algebra and in our review of college algebra in this class, and maybe use a couple of the new identities to rework problems, thinking about how we solve equations with exponentials and logarithms by combining functions to create one log, or combining things in a way so that we just had one particular variable. And so that's what we want to do today. And I think you'll find this very interesting, at least in terms of what we've been doing so far. So what I want to do, again, is to just do some examples of some equations so you can get a good feel for what we want to do. So I'll just say trig equations. It's a very broad topic. I mean, it's kind of like saying, college algebra equations. That could be something that you can do forever. I have students that send me emails. They're in engineering classes and they're trying to solve equations. I said, well, you don't remember that from pre-cal? And they said, no, can you help me? And I said, sure. So again, you'll be solving equations for the rest of your life. And so I guess we just have to be reside to the fact that we're stuck with it. So let's look at a very simple equation. I've got several here, but I want to look at something very simple that reminds us of college algebra. So say we have 2 cosine squared theta. And of course, the textbook likes to use theta. You can use any variable you like, but of course, when you're doing problems, we need to basically stick to the variables that are given to us. So again, just stick with whatever there is here. But if you're making your own problem, you can use any variable you like. So we saw on the last test that we can solve very simple equations, maybe in a particular interval. And so what we want to do in this case is compute all solutions. So when you think about this type of equation, you think about Professor Ron's lemma in the sense that we have to find all the solutions in 0 to 2 pi, especially since we have functions of period pi, and then we can extend them by multiples of the period. So the one catch about sine and cosine is that on the standard unit circle, they are not one to one. So if you have one solution in a particular quadrant, you can find another. And we saw that when we were working with the law of sine. So that's the only hiccup with the sine and cosine. And then, of course, tangent's a little bit better, cotangent. They just have a period of pi, but they're certainly one to one on those principal periods. So we always have to keep that in mind. So first, when you look at this, you're thinking, okay, well, the best thing to do in this case, let me align this a little bit better. The best thing to do in this case is to factor. So if we look at this, we're just going to go ahead and factor this as a difference of squares. First, we want something monic. So let's divide everything through by 2, just to make it simple. So we'll have cosine squared theta minus 1/2. And of course, 0 divided by 2 is this. I'm thinking of looking at this as a difference of two squares. You might be thinking square root property, but it's often simpler to think of it factoring this way, like we're factoring polynomials. And therefore, we've got a square here. And of course, 1/2 can be written as the square of 1 over square root of 2 squared. So we can think of 1/2 as 1 over the square root of 2 squared. So of course that's something on the unit circle. So at least we're not going to have a awkward looking answer, even though an exact answer may not look beautiful. It will still be, what we need, which is exact. So this will give us, using this identity, cosine theta minus 1 over root 2 cosine theta plus 1 over root 2 equals 0. So basically what we've done is we've just factored the difference of two squares. And when we do that, when we do something like this, we're thinking, okay, this is exactly what we did in college algebra. We could think of this as 2x squared minus 1, where that would just be an x minus 1 over root 2 and x plus 1 over root 2. And that would be pretty simple. We basically have already solved the equation there. But the only hiccup here, like I said before, this is not an x, this is a cosine theta, and likewise, this is a cosine theta. So now we have to think about the unit circle. So what does this mean? By the zero product, we have cosine theta would be equal to 1 over root 2 if we just transpose the 1 over root 2, or cosine theta equals negative 1 over root 2. Okay, so this is why we learned about the inverse trig functions. And then, of course, with Professor Ron's lemma, we can figure out the other solution in 0 to 2 pi and then attach multiples of 2 pi to them. Now, what we're going to see sometimes is that the solutions could be separated by a very convenient multiple of pi. So that will allow us to consolidate. It doesn't mean if we don't consolidate that it's wrong. It just means that our solutions may be redundant, that some parts of the solution contain other parts, and that's just repetitive, which we don't need. It's like writing a set, 2, 2, 2, 2, 2, when the only element is 2. But of course, we could be dealing with multi-sets and combinatorics, which that would be fine. So maybe that's not the best example, but I think what you can see now is repetition would not be something that would be very efficient. So when we look at this, we first remind ourselves, where does the inverse cosine live? Remember when we were defining these earlier? These live between 0 and pi, okay? And so when we get an answer, it's going to live either in the first quadrant or the second quadrant, okay? So that's really important. So now we have theta will equal the inverse cosine of 1 over root 2. Well, that's our friend in the sense that this is just pi over 4. So right now we're solving all of these in radians. When we do the triangles, we use degrees, but when we solve most of our equations, we use radians unless there's some direction to convert them to degrees. So we're going to be doing these in radian measure. So now we see theta, and we'll just call it theta 1 for now, will be pi over 4. And this is in the what? First quadrant, right? That's in the first quadrant. So when we look at this, we think, well, because the cosine function is even, we also have a solution that's equivalent to this in the fourth quadrant. So we can do Professor Ron's lemma and say theta 2 will just be 2 pi minus pi over 4. And of course, that'll be an 8 minus of 1. So that'll be a 7 pi over 4. So here's the other solution in the fourth quadrant. Now, just remember, even if these were horrible numbers, we would still know where they lived. We're just fortunate that these are on the unit circle, and that's fine. We're good with that. We like the unit circle. Okay, so when we see here, we've got two solutions in 0 to 2 pi, which are incongruent modulo 2 pi. That is, pi over 4 and 7 pi over 4 are not simple multiples of each other. So these are bona fide solutions. Now here, we can use the fact that we know this, or we can use the identity of the negative angle, which again, since this is fairly straightforward here from the range of the inverse cosine, we can go ahead and use this. So I'll state this way. So we have inverse cosine of the negative of 1 over root 2. Now, of course, if you got a little bit squeamish and thought, well, I remember this, but we also have an identity. So when you do the inverse cosine of the negative angle, that's pi minus the inverse cosine of the angle without the negative. So you can either use the unit circle directly, or you can just say this is pi minus the inverse cosine of 1 over root 2. But we know what that is. That's just what pi over 4. So this will give us pi minus pi over 4, which is 3 pi over 4. So of course you could have gotten that directly by just using the unit circle here, or you can use the identity. So that's your choice. I just want to make sure that you know you can use either. This is clearly in the second quadrant, as we know it should be. So we can call this theta 1. So again, unit circle directly to get this, or use the identity of the inverse cosine of the negative angle, which we talked about in 5.5. So now here you're thinking, well, Professor Ron's lemma, there's going to be another one in this particular case that will also work, and we can just subtract this from 2 pi. So theta 2 in this particular case will be 2 pi minus 3 pi over 4. And of course, this will be an 8 minus a 3, which is a 5. And this is in the third quadrant. Because in both of these cases, we know that the cosine is negative. Here, the cosine is positive, so we have these two quadrants represented. Okay, so this is what I was trying to say when we were working with the law of sines. And then, of course, when I put a problem on the test, bugs. When the rain comes, you get the bugs. What I was noting on the test is that I gave you a simple tangent equation. And I asked you to solve it in 0 to 2 pi. But again, the tangent is 1 to 1 on its principal period. So you don't have to do all of this. But it's important that we use Professor Ron's lemma. Now, here's what I was talking about. We have a consolidation process that we can do to extend. And again, this is just something that you would notice if you were reading a physics book or reading an engineering book and you thought, well, that's interesting. Why didn't they add multiples of 2 pi they are adding multiples of pi. Well, notice here, the pi over 4 and the 5 pi over 4 differ by pi. So I could add pi to pi over 4 to get that one. And so multiples, if I add multiples of pi k to this, I get both of these solutions and all the infinitely many. That's a consolidation process. And then 7 pi over 4 and 3 pi over 4 also differ by pi. So I could add pi here to get this. And then that multiple of pi k would give me all the infinitely many solutions that would be generated here. If I added 2 pi k to both of these, I'd have some redundancy. And so the idea is that we can consolidate. So this is something that I think is relatively interesting. And again, just a few more analysis, so to speak. So when we summarize everything, we can say now, and we can just separate our solutions with a comma. You can put these in the SmartPen videos. I put them in the curly braces, but it's your choice. Either curly braces or a WebAssign may just say, write your solution separated by a comma. So we can say in this case, pi over 4 plus pi k. Of course, we're going to use k to be an integer, okay? And then comma, and then we'll go over here and say 3 pi over 4 plus pi k. So this is a way to consolidate the solution so we get everything. And of course, as we add multiples of pi k, we get solutions here and solutions here. And as we add multiples of pi k, we get solutions here and solutions here and all of them. So we've extended to all solutions. So again, this is a way of consolidating. And again, since I've done this problem, there can be something that you can look out for when you do these types of problems. Again, it's not required, but it is more efficient. And it's just a little adjustment that makes your work good. Now, of course, you could also, and the commas are fine here, you could also do something like pi over 4 plus pi k in curly braces union 3 pi over 4 plus pi k. You could also think of it that way. But I think usually in your homework, they just ask for the particular solution separated by a comma. So these would be equivalent, but you always have to use the formatting. And I don't think the formatting requires you to use the curly braces, even though that's certainly something we could use and I've used often in class. Now, when it comes to solving problems, and let me just make a few comments here, and this is very evident when you do trig equations. We use algebra. We use algebra that we already know about. The only difference is that we have to remember that the objects are now trig functions. And so we have to use Professor Ron's lemma to navigate the actual lack of one-to-one of cosine and sine on 0 to 2 pi, which is the unit circle where everything begins, okay? So this is a nice fundamental type example that you'll use over and over when you do your engineering and your physics. And so a nice good example that covers lots of bases. Now let's look at some more algebra. Lots of times when you look at these equations, you're going to think of the types of examples you did in college algebra that were basically substitutions, quadratic in a particular function. So because you would notice that, you'd say, I'm going to try to factor this. And then you get a real simple example utilizing your knowledge of the quadratic equation. So in this case, we want to compute all solutions. Now, here's a good example where the solutions are not going to be neatly found on the unit circle, but that doesn't mean that we're stuck. It just means that our solutions are going to look a little bit different. So let's go ahead and write this down. This particular problem looks like this: tangent to the 4th power of theta. So we have the 4th power of tangent theta minus 13 tangent squared theta. So you can think of this like x to the 4th minus 13x squared plus a 36. So this is what I was talking about before, and why I like the fact that as we do the trig equations, we're really just going right back to the college algebra. So notice this is quadratic in tangent squared, okay? And notice, because it's quadratic and tangent squared, we can apply the AC method. So AC, that is A times C, is just 1 times 36, which is 36. And of course, we just need a negative 13. But then, of course, 36 is 9 times 4, right? Throw in two negatives and we've got it. So this falls out really fast. So Professor Ron's AC lemma gives us the factorization here that we can utilize for this particular equation. So in your notes, you can say this is quadratic in tangent squared. And like I say, we've seen this many times before, and because it's so simple, we don't really need to make a substitution. That's why I'm like, if you make a substitution, the substitution needs to be warranted, because if you're adding more stuff to the problem, that's just more things you have to navigate, and just makes the problem complicated more so than it needs to be. So now we can use this, and of course this is monic. We know exactly what goes in each of these parentheses. So we have tangent squared theta minus 9, and then we have tangent squared theta minus a 4. Now, of course, what's nice about this problem, at least at this point, is that 9 and 4 are perfect squares, but inverse tangents of those numbers are not on the unit circle. So that's what I was talking about. So now, just like the first problem, we have a difference of 2 squares here and a difference of 2 squares here. So we'll factor again. So we have tangent. We like it when it's easy, minus 3, tangent plus 3, tangent theta minus 2, and tangent theta plus 2 equals 0. So again, we don't have a Professor Ron's lemma for tangent because its principal period is pi and it's 1-to-1 there. So we don't have to worry about another solution on that interval. And that makes working with tangent very simple, okay? But if we're just extending to all solutions, we'll just add multiples of pi k and we're done. So that makes this a lot easier. So now we're going to set each of these to 0 by the 0 product. So if and only if tangent theta equals 3, or tangent theta equals negative 3, or tangent theta equals 2, always have to move the mouse out of the way, or tangent theta equals negative 2. So remember, we know that the inverse tangent lives between negative pi over 2 and pi over 2. So when we think about doing these types of solutions, and it's not good nor is it bad, we're just looking for all solutions. But we've all often found that if we have a solution in the fourth quadrant and we need to move it into the 0 to 2 pi, we have to add a multiple of the period. Maybe we have to add a pi or a 2 pi to put it in the positive realm, so to speak. So again, all of that's still on the table, but since we're not required to do anything specific here, we won't belabor the fact where the actual solution lives or terminates. So now theta here will be the inverse tangent of 3. This is a positive number. So, excuse me, this will be in the first quadrant. So this is in the first quadrant. Now we have theta equals inverse tangent of negative 3. But of course, we know that the inverse tangent is odd, so we can factor the negative. So theta equals the negative inverse tangent of 3, just the negative of this guy right here. And this is clearly in the fourth quadrant, okay? So we love the fact that the inverse tangent and the inverse sine are odd, so we can factor the negative. So very nice, easy to do. Now do the same over here. Theta will now be the inverse tangent of 2. Of course, that'll be in the first quadrant because this is a positive number. And then, of course, theta, well, let me run over to the next equation and not write the solution here. Move the mouse over. So now we have theta equals the inverse tangent of -2. And of course, we can factor the negative because the inverse tangent is odd. So we get negative inverse tangent of 2. And of course, this is in the fourth quadrant. Now, these are all incongruent mod pi. Okay, so again, we don't have to push this into the 0 to 2 pi. We're not required to do that. It wasn't specified that, excuse me, the solutions had to live in a particular region, even though we could easily do it. Now, when you look at this, you're thinking, okay, if I'm in a physics class and this is in radian measure, then maybe I can go to Google and get an approximation if that's required. Okay, or I'm thinking, okay, well, I need degrees. I need degrees, so I'll just do the 180 divided by pi, or use the degree mode on the Google calculator to do the conversion for me. Okay, so you have plenty of flexibility at this point. But now all we have to do is just extend all of these by the principal period, pi k. So if we separated them, all the particular solutions by commas, we would have the following, if and only if. So we have inverse tangent of 3 plus pi k, and of course this is exact, and this is really what we want. And if we need to approximate, we approximate once. Okay, don't throw in a bunch of decimals unless maybe the problem says, okay, approximate the 2 decimals or something. Comma, next one, negative inverse tangent of 3 plus pi k. That'll give us all the solutions, all the infinitely many based upon this solution. And then inverse tangent 2 plus pi k. Okay, and then lastly, the negative inverse tangent of 2 plus pi k. Now, what I've noticed here, and what you could also do, like I said before, these are all in radian measure. And if you need approximations, you can do that. If the problem requests that, then do that. Otherwise, these are all the solutions in exact, and you could think of putting these in curly braces with the union symbols if you like. But this gives you all the infinitely many solutions that solve this equation. Okay, and so what's interesting about all of this is that if you wanted to run all of these into 0 to 2 pi, okay, if the problem said, okay, I'm gonna throw a kink into this, and you wanted all the solutions in 0 to 2 pi, so we'll say 0 to 2 pi, okay. So say we're just saying we want solutions here, solutions in 0 to 2 pi. Okay, well, 2 of them we already know. We've got these 2 in the first quadrant, so we're done. Now here, of course, we just have to add a multiple of the period, which is pi, to push that into the what? Second quadrant. So if we wanted just 0 to 2 pi, we would take this one as it is. And then we would add pi to this one. So we'd say negative tangent of the inverse tangent of 3 plus pi. So that would push us into the second quadrant. This one's in the first, so it's fine. And then, of course, this one we need to push into the second quadrant. So we would say negative inverse tangent of 2 plus pi. Okay, so this would give us our radian measure in 0 to 2 pi if the problem asks for that. Okay, so I want you to feel flexible with these problems, because you may run into these problems in a physics class. And then, of course, if radian measure wasn't what you wanted, you could multiply all of these by 180 over pi and convert them to degrees. It's just that easy. The thing is that we like degrees in certain types of problems, especially when we work with triangles. So we're thinking if we need to convert, and then I'll just say multiply by 180 degrees over pi to convert to degrees. Okay, so that might be another thing that we need to do. And we could say, again, if we do that, let's just write it down. Inverse tangent of 3, 180 over pi. That would be the degree measure. And then this one, we'd have negative inverse tangent of 3 plus pi times 180 degrees over pi. Likewise here, inverse tangent of 2 times 180 degrees over pi. And then lastly, the negative of the inverse tangent of 2 plus pi times 180 degrees over pi. And this would give us degree measure, which would be analogous to what we have here, radian. So this would be degrees, and these would be radian. So radian, degrees. So this is often what you have to do when you're solving problems. The problem may just say, here, give me all the solutions. Or if you're solving a particular problem where you need to isolate certain solutions, maybe 0 to 2 pi, then you make sure that all of these solutions exist there. These two are easy. From the inverse tangent, we know where they live. These have to be adjusted by adding pi to push them from the fourth quadrant where we've got a negative value into the second quadrant. So that's what we do here. And then of course, if the problem required degree measure, we could just multiply all of these by 180 over pi and we're done. So there's nothing new here. That's why, I have to kind of go back and say, I don't really like the triangles that much. I really do, because the triangles basically introduce the concept of the degree measure and how you can toggle between the two. And so again, we're creatures of habit. We really do like the degree measure with triangles. It's just that's what we're accustomed to. And that's what we're used to. And you talked again to professionals in other areas, say in electricity, like electricians, plumbers, welders, things of that nature, where they are skilled artisans and they think in degrees. Again, because that's a very common way to characterize angles, and we've grown up with it. So that's an interesting example. Okay, now what I want to do is just do an example where, again, we capitalize on the algebra of the situation. And then I want to talk, I think I've got an example here where we're going to do some multiple angles, just so we can navigate that. That's not really hard, but I want to be able to use our lemma too. So here's an example that really doesn't fit into any category except algebra. So let's do it. I tried to pick some problems that will allow you to use what you already know and then throw in maybe a few identities. So here's an example. So here we want to compute all solutions. Compute all solutions. So we have 4 cosine theta times sine theta plus 3 cosine theta equals 0. Now, when you think about what we're doing here, we're like, okay, we're probably going to have to use Professor Ron's lemma because we got the sines and the cosines, and we're like, all right, so we're pretty much stuck with that. But what we notice here is that there's hope for solving this. Again, I'm always going to give you problems that you can solve, ladies and gentlemen. When you get to calculus and you discuss Newton's method, there are techniques in approximation. When you get to certain equations that require an approximation method, basically because the algebra it will only take you so far, and then you're saying, okay, well, I've got to do some calculus here to see if I can actually get a solution approximated to maybe 2 or 3 decimals. That's all I need with the problem I'm trying to solve. And so that'll be something you'll talk about in calculus. So for now, we will focus on the problems that can actually be solved with the techniques that I've taught you. So just be aware that when you get to some more engineering and more physics classes, there'll be some approximation techniques that you will use. And one of the most simple but very useful ones that's also second order is Newton's method. And it's remarkably simple and has a really interesting geometry to it. So you get to look forward to that in Calculus 1. So now what we're noticing here is that we have the cosine theta common to both. So we're thinking we can use the zero product. So what I'm going to do is say, just like we've done before, let's go ahead and factor the 4 cosine theta and see what we get. So here we've got a 4 cosine theta, just trying to think of monics, so to speak. And so when we do that, we left behind with a sine theta. But here, of course, we've just got a 3/4 because we have to pay for factoring. So now when we multiply back through, the 4's absorb and we get the 3 cosine theta. And of course, we get the 4 cosine sine theta here. So again, we're just trying to make the factors very simple. And now, of course, this 4 is just in the way. If you want to divide by 4, we just get rid of it. So this is cosine theta times sine theta plus 3/4. Now, again, when you determine your radian measure solutions, you want to write an exact answer. And then, of course, if you like, you can approximate them, just like I said on the last problem. So just like when you solve the triangles, write down your exact solution. Okay, so you have a premise, and then go to your Google calculator. Okay, so you have one level of approximation. And I know some of you, you've got your really nice calculators and you can store numbers with 12 decimals on them, and I'm sure that's convenient. So I mean, you can also do that. But I still like to see the exact solution on your paper so that I see that you understand the process. So now if you look at this, we've got the zero product. We can set each of these factors to 0. And then of course, when we're on one of the axes, we don't need Professor Ron's lemma, and we're glad for that. So let's just see how this turns out. So we have cosine theta equals 0 because we've got the product equal to 0, or sine theta, and of course transpose equals negative 3/4. So again, we see good old Professor Ron's lemma right here. But here, these are on the quadrant. These are on the axes away from the quadrant. So we're thinking, when does cosine theta equal 0 and 0 to 2 pi? Well, that's easy. That's at pi over 2 and 3 pi over 2. So we're thinking, okay, that's just going to be what? That's just going to be odd multiples of pi over 2. So just like we were thinking of the domain of tangent. You don't want cosine to be 0, so you want to avoid pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, all these odd multiples of pi over 2. So this one's done. We just say, okay, this is an easy one. This says theta is just odd multiples of pi over 2. That's done. We've covered this many times. And so we don't have to apply the Professor Ron's lemma because these are not in the quadrants. These are on the axes. So again, it's the same thing with sine, pi k. I mean, when is the sine 0? Multiples of pi. So that we don't need any special theory because those are just trivial cases. All right. Now, here we're, okay, so we're check, right? We're done here. So now we look at this and say, well, what about inverse sine? If we just have plain old inverse sine of x, where's that going to live? That's going to live between negative pi over 2 and pi over 2. Of course, we include the endpoints here, and this mimics what we have for the inverse tangent. Again, the sine, inverse sine, and the inverse tangent have that nice relationship. And plus, we get the nice odd relationship because we've got this really nice symmetric interval. Well, not so much here, but -1 to 1 for the domain. And then, of course, the real line is as symmetric as you can be, which is the domain of the inverse tangent. So let's face it, these definitions turned out to be very useful, and we rely on them. Okay, so now we have theta will be the inverse sine of -3/4. Okay, now again, this is odd, so we can factor. So we can just say theta 1 equals the inverse sine with the negative of 3/4. I'm just going to put theta for now because I may change it up. Notice this is negative. This is in the fourth quadrant, just like with the tangent. So if you wanted to push this up, so to speak, into the 0 to 2 pi to use Professor Ron's lemma, we can do that. So again, remember when we use Professor Ron's lemma and we've got the sine function, we've got to be either in the upper arc 0 to pi or in the lower arc pi to 2 pi to use Professor Ron's lemma. So this is kind of like, all right, do that. So now we can say this is congruent to negative inverse sine of 3/4. Here, let me write that 4 so it looks like a 4, plus 2 pi. Now, when you look at this and you think about this particular example here, you're saying, okay, we've just basically revolved once around the unit circle, but this puts us in the fourth quadrant where this is a positive number. And we'll say this is element of fourth quadrant and greater than 0. We need that. So now we can apply Professor Ron's lemma. So this is our theta 1. And then theta 2. Now, of course, we're in the lower arc, so we have to subtract this from 3 pi using Professor Ron's lemma. So this will be 3 pi minus, so we have inverse sine of 3/4 plus 2 pi. So of course we have a 3 pi minus a 2 pi, so that's a pi. And then of course we have minus minus, so we get plus inverse sine of 3/4. Now, what's interesting about this and what we're seeing here is that this is the solution in the fourth quadrant, and this is the positive solution in the third quadrant. That's Professor Ron's lemma, because we know that the sine function is, again, has that nice odd property. So if we have a solution in the fourth quadrant here, we have the automatic one in the third quadrant, which is this one here. Unlike the cosine function where they move like this, the sines move horizontally. So the idea here is that if we want to use Professor Ron's lemma, we've got to be in the 0 to 2 pi range. So now we can say here is a solution in 0 to 2 pi, and here's the companion solution here in 0 to 2 pi in the third quadrant. So we can call this theta 2. Now, here's the deal. If you need to approximate these, you have the exact solution right here, exact. And of course, you can use your radian mode here to get a maybe 2 or 3 decimal approximation. And then of course you can multiply by 180 over pi to convert to degrees, or just use the degree mode. So now when we write down all the solutions separated by a comma, we have pi over 2, 2k plus 1, And then we have our first solution here. So we have negative sine, inverse sine of 3/4 plus 2 pi. And now what you can do in this case is just go ahead and tack on 2 pi k. Now, if you want, you could factor this and make it look beautiful if you want, but it's not required. This, this is the theta 1 part, and this is tacking on the multiples of 2 pi, which gives you all solutions. So remember, this is the theta 1 right there. Now, if you want to keep these separate so you have that nice copy of theta 1 visible, then write it this way. If you combine it, then you lose that. Now, the last one will just be this one. So we have pi plus inverse sine of 3/4. Now we tack on the multiples of 2 pi k. Again, this is the theta 2 right here. So we use Professor Ron's lemma to find all of the zeros of this sine equation in 0 to 2 pi. And then once we have that, these in the red boxes, we tack on the multiple of 2 pi k to get the infinitely many solutions. And then of course, this one was just easy. So that was nothing to do there. So put this on a note card, like, cosine theta equals 0, boom, so you've got that available. Just like, for instance, if you have, let's go ahead and write down the one for sine since it's so easy. If we have sine theta equals 0, this just means theta is a multiple of pi, because that gives us all the zeros on the x-axis, okay, where we know the y-coordinate is 0. So when you have the cosine equation equal this one, where we have cosine theta equals 0, you have two very simple solutions that you can automatically write down, all solutions, okay? Or if you just want 0 to 2 pi, pi over 2, 3 pi over 2, or 0 and pi. That's it. So this should never be an issue for you. Again, this is what we call a fundamental concept, okay? Professor Ron's lemma, a fundamental concept. So what makes the problem challenging is that we've got all these concepts that converge into one problem. So again, if you wanted to approximate these here, you can easily do that. So if your homework problem says approximate to 3 decimals, you can do that. Now, what I did here, I went ahead and approximated these with Google with the radian mode. And for this one, I get to 2 decimals, you get 5.44. So the problem may ask to approximate this, which again is kind of a waste, but that just gives you the radian measure in this case, where we see we're in the 4th quadrant. So this is 5.44 radians approximately in the 4th quadrant. And this one, I use Google, and you get 3.99, which is in the 3rd quadrant. So if you were asked to give an approximation of these two, you have it, then you tack on the multiples. Again, this is really not very, very precise. If you're looking for an approximation, you have it, but when you write your answer, this is certainly the more acceptable version, because it gives you exact for any multiple of 2 pi, and is certainly preferred. This, if you're looking for a specific decimal approximation, again, in the 4th quadrant and the 3rd quadrant, fine. But when you do your general solution, this is always preferred because there's no round off error in it, and it gives you a first level approximation if you need it. Okay, so good. Now, what I want to do, and this is going to come back to one of the lemmas that we did last time. I gave you that lemma about adding sine and cosine, okay? Lots of times when you're doing trig equations, you're thinking, well, do I have to square this? Make it simpler. Then I have to worry that I might have introduced extraneous zeros and check everything. And the thing that I like is that if there's an opportunity to avoid that, do it. Often squaring is a wonderful technique. We really like it, but if we can avoid it with solving equations, that's also good too. But we certainly don't. We don't look at it with disdain. But when we're dealing with trig equations, that's just one extra level of difficulty that if we can avoid, let's do it. So here's a neat example of that. And I think it's interesting. Lots of times when you look at problems like this and you think about them, you're like, okay, what did we learn with the identities? We learned how to rewrite sums of sine and cosine, first level, first power, and then we learned some double angle formulas. So let's do the cosine and sine, and then I want to do a double angle formula where we basically use a trig identity to rewrite the equation to make one trig function. So here's the first example. So we have cosine, a very simple one. Of course, the ones I did last class, the numbers were terrible. And you're probably thinking, Professor Ron, give us some nice numbers, would you? Okay, so I'm going to give you some nicer numbers this time. I will hopefully be in your better graces. So now when we look at this, we're thinking, okay, this is that lemma. This is the a sine x plus b cosine x, but now instead of x, we're using theta. So what I'm going to do is I'm going to write it in the order of the lemma so we know what a and b are. So this is a nice example of using the lemma without having to square. So remember, we had a sine x plus b cosine x equals the square root of a squared plus b squared sine of x plus phi, again, where tangent of phi equals b over a. Okay, yeah, that phi looks pretty bad. Let me work on that. So what I kept saying is that the phi, and if we think of the AB as a coordinate pair, they have to terminate in the same quadrant. They have to live in the same quadrant, so to speak. So if this is going to make any sense, we have to keep track of what we get for this. And just like we've done before, we have to move it into the positive realm if necessary. Okay, that's really important. So now we can see here that a equals -1 and b equals 1, the coefficients here. And now, of course, instead of x, we're using theta, but no big deal. So now -1 comma 1, that's in the second quadrant, right? That's just our number theory, our general math class, right? So when we look at this, we're like, okay, so we've got what tangent of phi will just be b over a. So that's going to be what, -1, right? So we have phi is, and of course we can go ahead and factor, but let me write it, inverse tangent of -1. But this is what? This is negative of inverse tangent of 1. Okay, now this is in the fourth quadrant. This is in the second quadrant. So what we need to do is we need to add pi, because we know this is negative pi over 4. This equals negative pi over 4. Even if we didn't know, we would know exactly that it's in the fourth quadrant. So we set phi equal to negative pi over 4. Oh, too many slash lines. Negative pi over 4 plus pi, it's congruent, plus pi, which gives us 3 pi over 4, which is congruent to this guy, this solution, which is in the second quadrant, okay? So like I said before, we must have the AB and the phi in the same quadrant. So if we have to adjust this, that's the only hiccup with this. But we know in mathematics, if we just blindly do something, especially when we're solving equations, we get nonsense. That's the tough thing about solving equations. I'm sure a lot of you say, well, I'm going to do it this way. I'm going to try this. And then you think, well, it didn't quite work. I didn't get the same response that Professor Ron did. Let me see where I slipped up, or maybe I can adjust this. we always have to make sure that we follow all the rules, and that can be frustrating and somewhat awkward at times when we think we've got all of our ducks in a row. So now we've got the phi that we need for the lemma. And of course, we've got the a and the b. So this just means that what a squared plus b squared square root is just square root of 2, right? We just have 1 plus 1. So now we're good to go. So we've got, let's fill it in. This is replaced using the lemma. So we have square root of 2 sine of theta plus phi, which is 3 pi over 4. Again, we lucked out. We got the unit circle. I was good to you, equals 1. So now this is where we have to be a little bit careful because we've got to use Professor Ron's lemma. So now, equivalently, so we've made an equation, everybody, that is easier. This is easier using the lemma. Didn't have to square anything. So now we get sine of theta plus 3 pi over 4 equals 1 over root 2. Okay? So when you think about this and you think about what we need to do, we've got to apply Professor Ron's lemma, but first we have to get a solution. So first off, if and only if, let's apply the inverse sine, theta plus 3 pi over 4 equals the inverse sine of 1 over root 2. Well, this is nice. We know this is in the first quadrant, but we know exactly what this is. This is just pi over 4. I mean, duh, we know that's what we were going to get. So we've got what? Pi over 4 in the first quadrant. And if we didn't know that, if this weren't a nice number, we would still know that it lived there. So this is in the first quadrant, upper arc. So we're going to have to use Professor Ron's lemma after this. But now when we look at this, we see, okay, so this says theta equals pi over 4 minus 3 pi over 4. So again, if you like, this is going to be negative 2 pi over 4, which is negative pi over 2. But this is congruent if you add 2 pi to 3 pi over 2. Okay? So when we look at this and we think about this, you know, it doesn't mean that we don't want to have a negative answer or whatever. That's okay. We just mod out by 2 pi here to get this. Now, secondly, this is in the upper arc, so we can get the other solution in quadrant 2 by subtracting this from what? Pi. So this is our theta 1. Then theta 2. Oh, let me write it this way. Before we get to theta 2, I need to write the original equation. So now theta plus 3 pi over 4 will now be equal to pi minus pi over 4. So that'll be the solution in the second quadrant, which is 3 pi over 4. So again, when we look at this, we're thinking, okay, we have pi or theta plus 3 pi over 4 equals pi over 4. This is in the first quadrant. And then we use Professor Ron's lemma on this one to get the second quadrant. Okay, so again, from here, first quadrant, second quadrant, using Professor Ron's lemma. So this is how these are attached. And so then what we can see is that the 3 pi over 4s, they will absorb. So this will just say if and only if theta equals 0. Now 0 is fine. That's just multiples of what? 2 pi, right? Because in that case, we're thinking, what do we need? What do we need to be able to make this work? Well, if we take 0 and we add a multiple of 2 pi and then another multiple or negative multiples, we get all the solutions, just like we're going to have to do with this one. So we've got this base solution and this base solution. So now this says 0 plus 2 pi k, or you don't have to write the 0. So this will say if and only if 2 pi k, again, k is an integer, and then 3 pi over 2 plus 2 pi k. And we're done. So what's interesting about this, and if you like, you can, again, you can think of these as curly braces. It's another way to think about it. But I know a lot of times you just have to write your solution separated with a comma like that. So again, what we're seeing here is that, again, the sine function is not one-to-one. So this argument that we have here, when we apply the inverse sine, will be equal, in this case, to the inverse sine of 1 over root 2. We know that's pi over 4 from the unit circle. That's in the first quadrant. And then to apply Professor Ron's lemma, we know we also have a solution right over in the second quadrant. Okay, and so we apply Professor Ron's lemma by subtracting this from pi to get the second quadrant, and then that allows us to solve for theta, theta 0, and there we have it. So this is a more complicated problem in the sense that we avoid squaring. Squaring is fine, but you square and then you've got to check things, and then you've got stuff that really doesn't solve the original equation. This utilizes this particular identity here that's very user-friendly. Okay, very user-friendly. And we like this because this creates one sine function from a sine, the sum of a sine and a cosine. Now, of course, this takes a little bit of getting used to, but I kind of set you up for this with the last lecture by providing the premise for this. Again, this is just an alternative to squaring, because avoiding that is actually quite useful at times. It keeps everything on an even playing field, and you don't have to worry about going back and checking. Now, that doesn't mean that you'll never have to do this. Maybe squaring would be the only way to move the problem forward. But this is an excellent application of this particular identity. And you will also use this in calculus too, to avoid using the Weierstrass substitution. Again, this will be a quick method for doing an antiderivative if you have a denominator that looks like that. So there are many uses for this lemma. You will certainly see this beyond this course many times. Now, the other problem I wanted to do before we do the multiple angle is just a simple application of another identity that we talked about at the last class. So, for instance, say we have, and in this case, again, compute all solutions. Compute all solutions. We noticed with the last problem, the solutions were nice and user-friendly. They were on the unit circle, so don't count on that. But when it happens, we're certainly happy. So we have cosine of 2 theta. That's cosine of the double angle, right? Equals 3 sine theta minus 1. Now, I did the lemma on the last problem to kind of get you primed for that, to use the lemma, make sure that the AB and the phi terminate in the same quadrant, use Professor Ron's lemma. Okay, now what we want to do, I don't think is as involved, but it still involves noting the fact here that we've got an equation that has two different trig functions in it. The last problem, we combined the cosine and the sine into one sine function. That moved the problem forward, because it's like taking a bunch of logarithms and combining them so we can use the definition of logarithm. Same technique we used in chapter 4. So when we look at this, we're thinking, okay, we have a form of the double angle which actually involves the sine. So let's just remind ourselves, remember I like saying cosine of the double angle, and we saw how we got 3 forms of it. So remember we have cosine 2 theta. That was cosine squared minus sine squared. But what we did is we replaced the cosine squared with 1 minus sine squared, and we got this second form here. And remember, we use these to write the power reducing identities. So the cosine of the double angle is a very, very important identity, especially in the calculus. We live to use it. I mean, we're like kind of stuck with it. So when you look at this, this is one of the forms that we talked about last class. So this is very important. This gives rise to the double angle. I mean, the power reducing, like I just said, very important. So now what we can do is say, if we have the opportunity to replace cosine of the double angle with this, we can create a quadratic equation in sine, which we know how to solve. So now we can say from here, if and only if, we'll get 1 minus 2 sine squared theta equals 3 sine theta minus 1. So again, we look at this and say this will now be quadratic. Just like we started out, quadratic, we had quadratic in cosine, we had quadratic in tangent squared. Now we have quadratic in sine theta. How simple. So now let's just throw everything on one side and keep our fingers crossed that it will factor. So we have 0. So we'll have a 2 sine squared theta. We've got the 3 sine theta, which is already hanging out. And then, of course, we subtract 1 from -1 and get a -2. So again, quadratic in sine. But now we see that Professor Ron's lemma is good. We've got what? AC is what? 2 times the -2. And then, of course, if we think about that, we're thinking, okay, that's a -4. 4 times a -1 gives us 3. So this will be what? 4 times a -1. So we just think of this as a -4 and then rewrite it with this very simple factorization. And the sum of these two factors is 3. So you could probably see that before I did all of this. So now we're good to go. We don't even have to do the factoring by grouping because it's so simple. So we have 2 sine theta. So we need the 4, so we'll have the 2 here, and then we'll have the -1 here. Okay, so we get the 3 sine theta, we get the -2, and we get the 2 sine squared theta. So that's a simple factorization. Now, of course, the more complicated problem would be the quadratic function, and then, of course, that's just extra work, but it doesn't make the problem necessarily that much more difficult. When we're already dealing with numbers that aren't on the unit circle, where our solutions get more symbolic, but that's okay. Symbolic solutions are exact, and that is always preferred. So now we're like, okay, this is like the beginning 2 problems we did. We've got the 0 product. So now we can say if and only if 2 sine theta equals 1, that's for this one, transposing the -1 to the other side, or sine theta equals -2. So again, transposing the 2 to the other side of the equation. So now we're looking at this and say, okay, we're back to square one. We're back to Professor Ron's lemma. So this is easy. Now, of course, this is outside of the range of the sine function. And if you, again, we're trying to apply the inverse sine to this, the inverse sine function has a domain of -1 to 1. So this one has no solution, which is fine. I mean, we'll take it. We'll take what we can get. So no solution there. So this particular factor does not provide us any thetas that will actually solve this equation. And let me also note the following, ladies and gentlemen. We simply made a substitution here. We didn't square anything, okay? We just made a substitution. So we have not introduced extraneous solutions in this case. So what we see here is that this particular factor doesn't give us any thetas, but of course we can see we'll get some here. So if and only if sine theta equals 1/2. So don't we wish all of our problems would be this easy? You know, what's interesting about these problems, if we think about the last one, we have to be careful in applying Professor Ron's lemma and then solving for the new angle, which was a sum function. Okay, so you have to apply the results in a fashion just like we always do. Don't change up the routine, because if you change up the routine, you're changing the mathematics in a very real way, which introduces an error. So keep everything nice and consistent. So now this says theta is the inverse sine. Now you can see how I have just been saying so much about the inverse trig functions. They are imperative. If you got tired of it, I can't apologize for that because they are so critical to what we're doing. And when I talked about them the first time, I said, I know this seems dry and boring, but they are imperative. They are the essential tools for solving equations. Without them, and without knowledge of them or correct knowledge of them, all of this falls apart. So again, when we think about doing calculus, we've got to be able to create the calculus of the trig functions. And that's going to mean that we're going to have to solve equations. And if we don't understand the trig functions, at least on a basic level, we're not going to be able to move any of that discipline forward. So now this is a nice number, isn't it? This is just what, pi over 6. This is on the unit circle. Okay, so we can say this is our theta 1, and this is in the first quadrant. So nice and simple. So now theta 2, by Professor Ron's lemma, will just be pi minus pi over 6. Again, that's going to be 6 minus 1. So this is going to be 5 pi over 6 in the second quadrant. Again, if we have a first quadrant angle, the sine function will also give us a second quadrant angle by via subtraction of said solution from pi, or 180 degrees if these was all written in degrees, but that's not usually the case with these types of problems, except the triangle problems we know different. So now when we look at this, we're pretty much done. We just tack on the multiples of 2 pi k, we're done. So equivalently, we have pi over 6 plus 2 pi k, and we have 5 pi over 6 plus 2 pi k. So I think this is a really nice example that gives you a reason for knowing certain trig identities. Okay, you will find, as I've said before, as you work through calculus, certain identities will come up over and over again. And you will put these in your memory bank. And then once you're done with your education, at least in the school sense, and now you're going to be educated on your job, you'll remember these because you'll probably have to use them again. But the key to all of this is just use. When we use things, they become part of our long-term memory. When we don't, we have to use our reference manuals and our online reference manuals to jog our memory because we don't remember everything. Now, one thing that can happen that I like about trigonometry is that we sometimes get multiple angles. For instance, instead of theta, what if the argument is 2 theta? Like we saw in the last problem, we got rid of the double angle by using a trig identity. But what if we have a very simple problem that has a multiple angle, like maybe 3 theta? How do we navigate that? Well, it's a very simple way to do that. We don't really have to involve any new theory. We just have to keep track of the fact that when we actually extend to all solutions, we make a division process. So this is what we call a multiple angle. We saw it on the last problem, but we got rid of it. So we didn't have to deal with it. So let's just take a simple example. And this is what the text will often do. And then for this particular one, I'm going to modify how we write the solution. We're going to write down all the solutions. So I'm going to say all solutions, and solutions, we're going to restrict solutions in 0 to 2 pi, just as an additional part of the problem. So let me just say this, ladies and gentlemen, once you figure out all the solutions, you can always restrict to some other interval and just start, iterating by the multiples. And then once you pass that interval, you stop. So you get all the solutions in a particular interval. So that's what this is doing. So there is utility to writing down all solutions in some cases. So here's an example. This kind of reminds you of the problem on the test, but without the multiple angle. Yeah, that was always nice to see how things fit together and how we just keep saying the same thing over and over. I guess good because it's, eventually it sticks. So notice here, we've got all the ingredients of a tangent equation, but instead of just the regular theta, we have a 3 theta. So let me show you how to navigate that. First, we're just going to move everything over. So we have square root 3 tangent 3 theta. Now, if you like, what I'll do in this case, you can move everything over, or you can go ahead and factor it. Let's just factor it. Let's factor the square root of 3. Let's try it that way, just to be consistent with what I've been doing with all the problems. So if I factor the square root of 3 here, I'm going to get plus 1 over square root 3. So that accomplishes the same thing, which is probably a little bit more like what I've been doing. I just factor things, and that's probably a lot easier. So now when you look at this, of course, the square root of 3, that doesn't have any bearing, but now we see we have this equation here by zero product. So if and only if tangent of 3 theta equals -1 over root 3. And that's a point that we see on the unit circle. We can combine the x's and the y's to get that. So this is going to be simpler. So now at this point, we say, okay, well, this is going to say that 3 theta is what? The inverse tangent of -1 over the square root of 3. But of course, the inverse tangent is odd. So this is going to be in the 4th quadrant. So this will be the negative inverse tangent of 1 over root 3. Now, when you look at this and you think about this particular problem here, you're thinking, okay, well, inverse tangent of 1 over root 3, that's when the cosine is root 3 over 2. So that's going to give you the 1/2 of the sine. So this is going to be pi over 6 with a negative. So this equals negative pi over 6. Now, just to make our solutions look nice, we're going to mod out. In this case, we're going to mod out by pi. So this will be congruent to negative pi over 6 plus pi, which gives us 5 pi over 6. So this solution is actually in the 2nd quadrant, and it's positive. So that makes for a prettier solution, so to speak. So sometimes when we're writing things and we know eventually we're going to have to end up in here, we might as well make sure that where we're starting is at least in that interval once we make some adjustments. So let me just kind of recap everything. Nothing has changed. Everything I've done is what I've done before. So we know that the goal is going to be this, at least when we restrict. So we apply the inverse tangent, we apply the fact that it's odd, and then of course we use the fact that this is a ratio that we find on the unit circle, namely pi over 6 with a negative pi over 6. And then of course that's in the 4th quadrant. Let me just write this. This is in the 4th quadrant. So we can mod out by pi, in this case, to get an equivalent. Again, we're just saying that the argument equals this, okay? So we're just treating this like a regular old phi or whatever. It's just the argument. Okay, now we've done the problem just like we always do. Now we extend. That is, we think, okay, if we want all, and this is critical. So I want you to do these problems this way. If you don't, you will forever get them wrong. So work the problem just like that. We're just a plain old phi, doing everything like you normally do. Now we want to extend to all solutions. What are all the solutions in this case? Well, we have to add multiples of the period. So that's pi k. So equivalently, for all solutions, and this is very important, you can go ahead and write the new period, but I found that teaching it this way is usually a little bit easier for everyone. So you say 3 theta equals 5 pi over 6 plus pi k. Because if you go ahead and try to divide and then add multiples of the new period, that's fine and that works, but this is a little bit easier to execute. And so now we can find theta by dividing these two terms by what? 3. So all solution and then division. So this is the extension. And so we have theta will be 5 pi and 3 times 6, that's 18, plus pi over 3k. Now, this is not very user-friendly. So what I tell my students to do is just like when we do transformations, which a lot of you didn't do on the test. When I told you to graph things, I said, I want you to move the points and the asymptotes like I did in class. Maybe 2 or 3 of you did it. The rest of you didn't do it and you lost points. So again, there's a reason why I ask you to do things, ladies and gentlemen. I ask you to do things so you can set up a mindset that's going to help you solve other problems. There is always a reason. So now, just like we're doing a transformation, let's get the same denominator here so it's easy to construct the solutions here. So we'll do 5 pi over 18. And then, of course, we'll get a denominator of 18. So multiply the 3 by 18. And that'll be, by 6 to give us the 18. And so we get 6 pi k. Now, of course, this reduces to this, but now the denominators are the same, and we can just bounce through the particular solutions. So now when you look at this, you're thinking we want 0 to 2 pi. So what is 2 pi in terms of 18? So that'll be 18 36 pi. Okay, so we can start with 0. That's our first solution. And we keep adding multiples here of 6 pi over 18 as long as we stay below 36 pi over 18. And once we expand beyond that, we stop. So this gives us the recipe that we need. Now, of course, this is all solutions right here. This gives you all solutions. So if you had to write all solutions, you can say 5 pi divided by 18 plus 6 pi over 18 times k, where k is an integer. I found that this method is the one that students have the least trouble with as long as they apply it in this order. Again, you are not required to do this, but I think it makes the logic a little bit easier. However you want to look at it is completely up to you. Just do it correctly, okay? And here's another thing too that a lot of you all ask about. It doesn't matter to me how you do the problem, but if you leave gaps in your logic and you just write something down with no support of it, I don't believe that. Okay, I don't believe that. You all are not at the level where you can make those kinds of leaps. It's not going to happen. And I don't say that as to be critical. I say that because you're still building your mathematical background. Okay, so if you leave a major logic gap in your reasoning, that's not correct. Okay, so if you're going to give me an alternative method, you need to support what you do in a correct manner. That's fine. Most of you seem to think that I require for you to do the problem the way I do it. I do not. I never have said that. I'm just saying that if you adopt these techniques, you're probably going to be more accurate and you're going to have a roadmap that will make the problem in general easier. So that's where I've been, and I've been there all the time. So if you want to quibble with that, that's fine, but it's not true. So now when we do 0 to 2 pi, we can just start here and add multiples. So let's do it. So we have 5 pi over 18. So the problem will probably be something like this, where we list all of them that live here. Okay, so now let's do 6. 6 plus 5 is 11. We can add integers, that's easy. Now we have 11 plus 6, that's 17. Now we say 6 plus 17, that gives us 23. And then 6 plus 23, that gives us a 29. And we're almost there. 6 plus 29 gives us a 35. So now what we can see, if we add another multiple here, that will take us beyond this. So this gives us the solutions that live here. Now, again, it's a whole lot easier to go backwards from all the solutions. And again, like I say, think about like we're doing transformations so that you've got common denominators here. The difficulty working with the pies, I mean, we're glad we have the pies, but sometimes the difficulty is just insurmountable if you're trying to get a common denominator in your head and navigate the arithmetic. Just go ahead and write it down so that the step here is very simple. So this gives you a nice blueprint of how you can actually deal with multiple angles. Now, the next one that I want to do is basically, and when I look at this, I've used the lemma, and I want to try this one. I don't think the lemma is the end all problem, but it offers us a way to do things that turns out to be very useful. And when I say the lemma where we add the sine and the cosine, if we end up with a multiple angle, we can use the same technique that we've used here. So use this one kind of as a blueprint dealing with multiple angles. So let's look at the next one and also consider Professor Ron's lemma. So this will be interesting. So here's an example with multiple angles that we're stuck with. So we have sine. So in this case, I'll just say, what do I want you to do? Go ahead and write all solutions, and then we may restrict. So I'll say all solutions, because these don't turn out to be beautiful numbers. And then let's see, what do I have here? All solutions, and then restrict to 0 to 2 pi. So we have sine of 2 theta equals 3 cosine 2 theta. Now, like I said before, the application of the lemma is nice. That is, we can avoid the problem of extraneous solutions. So let's look at this. We want to apply lemma. We love the ones that have all the nice quadratic. They're easy to do. That's like doing college algebra. But this requires us to know our trigonometry. So if and only if sine of 2 theta minus 3 cosine 2 theta equals 0. Now, when you think about this and you look at this, you're thinking, okay, well, we got a sum of the sine function and the cosine function with first degrees, so we can apply the lemma. But the numbers aren't going to be beautiful, but we'll survive. So now we've got what? A equals 1, and we have B equals -3. That is, put a 1 there, shadow 1. And so now we've got the point 1, -3. But notice this is first down to the fourth quadrant. So this is in the fourth quadrant. So when you think about this, we've been usually ending up in the second quadrant, but here we're in the fourth. So we need to make sure that we choose our phi to also live there. So now notice we have tangent of phi must be b over a. So that's going to be a -3 if and only if phi equals the inverse tangent of -3. But of course, this will be phi equals, factor the negative inverse tangent, because it's an odd function, of 3. Of course, this is a negative value, so we know this is below the x-axis in the fourth quadrant. So what we're seeing in this particular case is that we can set phi equal to this without a problem, because they correspond. So this is good. So now we can go back up to our problem and say, okay, what's interesting about this is as we look at this, we might say, okay, we're going to get some simplicity here because we've got this zero over here. So we're thinking, man, that's great. If there's a non-zero here, then we've got to work a lot harder. So equivalently, now let's go ahead and see what we get here, even though it's not going to make any difference. We get an a squared plus b squared will be a 1 plus a 9. So this equals 10. So we get a square root of 10, which isn't even going to matter. So we've got square root 10. So we use the lemma. Remember, we have, I'll write it up here again, a sine x plus b cosine x equals square root a squared plus b squared sine of x plus 5. So let me make sure you can see that square there. I'll extend the radical a little bit more right there. Okay. So now we've got what? We've got sine. So we've got this part, square root of 10, sine. And we have 2 theta. Again, look, got a 2 theta. And then we have our phi, which is what? Minus inverse tangent of 3. So, and this equals 0. So again, all we have to do is make sure that our point and our phi belong in the same quadrant, and we're good. So now, of course, we divide by root 10, that just goes away. So we have 2 theta minus inverse tangent of 3 equals inverse sine of 0. Now, here's what's interesting about this particular problem that makes it simpler. Notice we don't have Professor Ron's lemma here. This is just the pi k that I said before. We just say, okay, when is the sine equal to 0? Well, when you're at 0 or pi or any multiple of pi. So this actually makes the problem 10 times simpler. So I think what's interesting about this particular example is that we get the extension without having to do a whole lot of extra work. So now we get 2 theta minus inverse tangent of 3 equals pi k. Again, this is the simple solution because we're on the axis and not in the quadrant. So now we can actually solve for this. So equivalently, theta, 2 theta equals inverse tangent of 3 plus pi k. And now we can divide by 2. Now what, again, when you think about this, always navigate everything step by step. Say, I don't need Professor Ron's lemma, so just write this in. No use of Professor Ron's lemma. This is important. You don't need it because it's not required. We're not in a quadrant. And so now theta will be 1/2 inverse tangent of 3 plus pi over 2 times k. All solutions right there. Now, when you think about this and you think about how we navigate this, note, observe that 1/2 inverse tangent of 3 is in the first quadrant. So what we can do is we can add a multiple of pi over 2 to put us in the second quadrant. We can add another multiple to put us in the third quadrant, even without knowing what this is exactly, and adding another multiple to put us in the fourth quadrant. So that will exhaust this. So this is how you navigate this using the fact that we don't have an exact value. We have an exact value, but it's not a number value that we got from the unit circle. So now this will allow us to write the solutions that we find in this particular interval. So now right here, all solutions. and now 0 to 2 pi. So we'll start with this guy when this is 0. So this is set up just like the last one, but we don't need the nice denominator so much because we're not going to combine them like we did before. We're using the logic that we use from here. So this will be 1/2 tangent inverse of 3, 1/2 tangent inverse of 3. Now let's push it into the second quadrant. So we do 1 multiple of pi over 2. Okay. Now, of course, if we do 2 multiples of pi over 2, that'll absorb the 2 if you like. So that'll just be pi. So we have 1/2 inverse tangent of 3 plus pi. Again, if you like, this is k equals 0, k equals 1, k equals 2. So just go ahead and write it below. First quadrant, second quadrant, third quadrant, and then the last quadrant, k equals 3. So of course that'll be 3 pi over 2, ladies and gentlemen. So we get 1/2 inverse tangent of 3 plus 3 pi over 2. So the navigation of these problems doesn't have anything to do with us having a pretty number from the unit circle. We use what we know about the inverse trig functions, and that pushes the problem forward, okay? So like I said before, solving the equations, why is this kind of the last thing we do? Because we have to build up to this. Here now we're using everything. We're using the arithmetic. One thing I guess you're thinking, well, where are the triangles? Well, we've been using triangles, a lot, but here you don't need the triangles as much. You need the identities, you need the inverse trig functions, you need Professor Ron's lemma, you need the arithmetic of the unit circle. So basically solving equations is kind of like the pinnacle. And is there more to trigonometry? Well, you could spend some time with some other topics, but these are all the trigonometric ideas that you basically need for calculus. And so when you think about it that way, you're in good stead. Now, I've got an example here. I want to do one last example that utilizes one of our and it's not hard, it's easy, but we spent some time with some sum to product, and that was the very last thing, and you thought, my goodness, Professor Ron, I'll never remember these. And I'm not asking you to. These you need to put on note cards. So what I wanted to do was give you an example, because we've got this lemma where we add sine and cosine, okay? But if we've got a problem that's simple like this, we can still navigate it without using numerical methods. So here's the sum to product. That these were the last identities that we derived last class, and we saw that if we pick the alpha and the beta, then we can write the product here. So this would give us a product, which would most likely make our problem a lot easier. So here's what I want to do in this particular case. I want to use this identity in a problem. And your examples in your homework, they'll say use a particular identity. So I like that. They're trying to give you a leg up. And it's like on a test, sometimes I'll give you a hint. Maybe it helps, maybe it doesn't. But let's look at this example. I thought this was interesting. Again, not all identities get the same use, and they tend to fade from our memories. But here's an example. So I'll just say, in this case, yes, all solutions. So we've got cosine 4 theta plus cosine 2 theta. That's pretty horrible looking, equals cosine theta. So when you think about something like this, and you think about, what is this going to mean for us? And how is it going to make what we do easier or more difficult or whatever? What we're going to do is try to think about this in utilizing some of the identities that we've already talked about. So here's what I'm going to do. Let me go ahead and write this down so you'll see where it's coming from. We have cosine alpha, and of course this is rigged, so it works out. You know, we want the problem to work out, equals 2 cosine alpha plus beta over 2. You look in your notes, you'll see this, and cosine alpha minus beta over 2. So this is the sum to product. Sum to product, one of them, one of the four. So now, when you look at this, you're thinking, okay, well, at least on this side, I can try to manage this and maybe I'll end up with another factor of cosine and then yay, I can use the zero product. So notice here, alpha is 4 theta if we use the notation from our identity, and beta is 2 theta. Any order you like, it doesn't matter. We can always use the even nature of the cosine function to dispel the negatives, right? So now just go ahead and write this down. Alpha plus beta over 2. Here's our sidebar, so to speak. So this will be 4 theta plus 2 theta, which is 6 theta over 2, which is 3 theta. So we get to use multiple angle and all the goodies that we've talked about. And then alpha minus beta over 2. Okay, this will be 4 theta minus 2 theta, which is 2 theta over 2. And there's that theta that we were looking for. So that's happy days right there, okay? So now when we look at this identity here, we have cosine beta plus, cosine alpha plus cosine beta, we can use the identity. So equivalently, we have 2 cosine 3 theta cosine theta equals cosine theta. So that's what I was thinking. If we can maybe push into this problem here, this sum, a factor of cosine, then we can factor this problem and use zero product. So that was kind of the whole goal here. So now when we look at this, if and only if 2 cosine 3 theta cosine theta minus cosine theta equals 0. So this kind of runs everything into the proper realm. So now, for instance, if I had just given you this equation, this would have been like one we've already solved. So this now takes us to an equation that we have knowledge to solve. Notice we had to use the sum to product to make it a little bit more manageable. So what I was going to do is underline these. So we're going to factor and also the 2 here, so we can get a nice equation. So equivalently, we have 2 cosine theta, and this will be cosine 3 theta. I'll put the parentheses here just to focus on the 3 theta. And of course, this will be minus a half. So just go ahead and factor the 2. This will give us the negative cosine theta. And of course, this will give us the product here. So we can use, again, nice simple equation like we had on the last problem. So we have the 2 doesn't matter, just ignore it. Cosine theta equals 0, or cosine 3 theta equals 1/2. So now we get to use Professor Ron's lemma with the multiple angle argument, which you know how to do. And of course, this is the easy one. What do we get here? Remember, this is pi over 2, 3 pi over 2, 5 pi over 2, things like that. Odd multiples of pi over 2. So we're done with this. This just says theta equals pi over 2, like we're doing the last test, domain of tangent. That focuses right on this equation here, 2k plus 1. So that's easy. Again, remember, k is an integer. Now we're at Professor Ron's lemma with the multiple angle argument. So we have, just think of this as a phi if you want, just as a singleton, equals inverse cosine of 1/2. Again, this is a nice unit circle. We know inverse cosine of 1/2 is pi over 3. So what I would say here is that even if you don't have a nice unit circle angle, it doesn't matter. You still navigate everything the same way. Now, of course, we know that the inverse cosine lives between 0 and pi. So this equals pi over 3. And we know that's in the first quadrant. Now before we can go ahead and extend like we did before. Remember, we take this and we extend multiples 2 pi k and then divide by 3. So now we have 3 theta. This will be the first step of Professor Ron's lemma, pi over 3 plus 2 pi k. Do the extension. So I'll just write extension, and then divide by 3. So theta equals pi, 3 times 3, 9, plus 2 pi over 3k. Okay, that's the first part. Now, of course, remember, this is in the what? First quadrant. So we've got a solution here. So with the even of the cosine, we have another solution here in the fourth quadrant. So we subtract this from 2 pi. So we can say this is theta 1. So theta 2, or let me just start 3 theta, will be now 2 pi minus pi over 3 plus 2 pi k. We'll go ahead and do the extension in Professor Ron's lemma in one step. So we have 3 theta equals, okay, now this will be what? A 6 minus a 1, so that's a 5 pi over 3 plus 2 pi k. And now we can divide by 3. So theta equals 5 pi over 9 plus 2 pi over 3k. Now, like I said before, and if you want to go ahead and just add on a little subscript there for a mutually or an incongruent solution. That is, the thing is, when you use Professor Ron's lemma, you don't get a multiple of the first solution. You actually get a new solution. And so when you think about it, we're up here. So where the x is positive, if we move down here, the x is positive. Kind of like with the sine, if we have a solution here, then we can find another solution over here. If we have a solution here in the sine, then we can move over here and find a solution in the third quadrant. So when you think about Professor Ron's lemma, you're basically thinking about a very simple geometric construct. So now when we write all the solutions, so equivalently, and again, separated by commas, we'll have what? Pi over 2, 2k plus 1. Again, k is an integer. I think in your homework, k is utilized most. Sometimes n's are used a lot in calculus too, but just use whatever the problem suggests. Remember, the formatting is important. If you don't follow the formatting, you get that red X. So be very careful with the formatting. And then now, of course, we have the theta 1. So this gives us pi over 9 plus 2 pi 3 k. And then the theta 2, which we have right here. So we have 5 pi over 9 plus 2 pi 3 k. So I think what you can see here is that if you have a double angle or a multiple angle with another trig function, you're probably going to look to use one of the double angle formulas for cosine, because you want to get all the trig functions to be the same. If you have a setup where you've got a sine and a cosine of first degree added, there is an open door to use the lemma, the a and the b, the a squared plus b squared type thing with the tangent of phi equal b over a. That opens the door to that. When you've got something that looks really odd here, just remember that even though these are limited identities here, they are very useful, Because if we think about it, remember, ladies and gentlemen, we started with the addition, subtraction formulas. We got the product to sum. Those are, again, with these, easy to derive. But then from here, we did the change of variable, right? And we got the sum to product. So here, product to sum to product, very limited. I agree, very limited, but very useful. So if we're trying to utilize a technique, we can see here that this particular identity, as I've written here, is a way to open up a process to solve this equation. And so now what we see, we can analyze the alpha and the beta to get the correct arguments. And then, of course, we have a much simpler. So we just say easier. The idea is I will give you problems that you can solve. I'm not going to give you problems that require an approximation technique. Of course, you can always write down the exact answer. You'll have a method to do that, as we've done in this lecture. And then you might think, okay, well, the problem says give a 3-decimal approximation. We can go to your Google calculator and get that. But I want to just remind you that we have 3 basic constructs here. College algebra with Professor Ron's lemma, okay? College algebra with Professor Ron's lemma. Second, we have the lemma of adding the sine and the cosine with all the other stuff. And then third, we have the use of identities, okay, with the possibility of the multiple angle, okay? So when you think about problems in solving trig equations, you want to kind of dissect things. You want to look at things and say, well, is this really college algebra in disguise? Yeah, it looks like it. I'm going to apply algebra. Or do you need to take out the larger artillery? You've got a sum of sine and cosine. You don't want to square. So you're thinking, let me use the lemma. And then you may run up against something where you've got to use a trig identity to make it simpler. And then you've got the multiple angle. So what I would suggest with the multiple angle is to just treat this like one object, use your Professor Ron's lemma, extend first, then divide. You can go ahead and divide and then tack on the new period like we have here. That's not a problem. But what I find is that students divide to get this, and then they put the 2 pi k here and don't divide and forget. So I try to consolidate the process so you don't forget to do that. So again, find a method that works best for you, but try to do it in a way that you don't forget anything. And so, of course, this is a technique that can be easily employed and something that you will use over and over. It's really unfortunate to be in physics and the math is keeping you from getting the correct answer because you're ignoring something. So after pre-cal and a couple of semesters of calculus, you should be able to navigate university physics very well. And if you put the time into the math, you will groove with the physics. The physics requires the language of mathematics. And at Texas A&M, where I did my graduate work, the physics department was like the math department, really bad news for most students because they're so rigorous. And there were physics professors that would say, oh, well, maybe you should take this course here and then come afterwards. They would admit that their classes were really very challenging. And of course, the engineering calculus students, the labs that I TA'd, they would always talk about how challenging the physics was. Again, these would be the kids in the calculus 2 that would be taking physics 1. But at A&M, they would allow you to take physics 1, university physics, while you are concurrently taking Cal 1. At San Jac, we don't allow that. I agree with our philosophy at San Jac that you have at least the calculus 1 and you're concurrently taking Cal 2 when you take the first calculus-based physics course. Because it's really kind of hard, ladies and gentlemen, to be learning the calculus when you need to be using it. And it's like, well, I haven't got to that yet. Oh, don't worry about it. I'll show you how it works. Well, we all know that that's probably not the best way to do it. So as you solve your trig equations, think college algebra and just add the new ingredients that we've had in this course. So again, I will send out invitations for our conference hours today. Again, if you come by, that will be great. Otherwise, I will look forward to your WebAssign messages. And I will, again, there's going to be a little quiz problem, which is going to be a QEP signature assignment on the law of cosines, which I'll tell you more about. It'll be a way to get another quiz grade that again is always a good thing to do. And this will be the general education assessment that you've been doing in other classes. But I'll give you some information about that and let you know about that. It'll be a very straightforward problem and something that, you know, again, as long as you write it up by yourself, you can discuss with other students. So I appreciate your attendance today. I hope you enjoyed the excursion into trig equations. You'll enjoy working through this. And have a great day and enjoy the nice cool weather. See you.